So in fluid dynamics, there's something called viscosity. Now viscosity creates a shear stress if a fluid is flowing over a surface, right? And so that shear stress could be, if I have fluid flowing through a pipe, that shear stress could be pulling on the pipe. And that's viscosity causes that. And so my goal in my project was to test out, how do you test viscosity without having to take a water sample and bring it to the surface? I mean, they have instruments now that are very sensitive that can do it. My hope was to be able to create an onboard viscometer for an ROV that could pick up data almost real time, right? And so that's why I created this device. What this device does is it spins up this disc right here. It spins. And a motor, which is right here, causes the disc to spin. I made them independent because I wanted to isolate as much of the motor friction away from the disc. That way I could try to grab as much of the fluid dynamics on the disc. If you think about it, the more viscous the fluid is, the quicker my disc will spin down as soon as I disconnect my disc. Now the way I can find out the position data of my disc is I have it embedded along the disc magnets and a Hall effect sensor embedded in here. So it passes through that, sends a voltage out for all your positions, and then what you can do is you can extrapolate velocity and acceleration graphs and find out your forces that you have on your disc, and from there figure out the viscosity that you have. So I will now show you how to build this project and teach you all about the parts that you need. Okay, so let's talk about the things that you need to buy first, okay? You need to buy electrical tape. It is absolutely essential because with electrical tape you will use it to waterproof a 10 to 12 volt DC motor. This you'll also need to buy. It's usually about $5. Because our system uses a disc that spins around, we're going to try to reduce as much friction as we can. So to do that, we have two types of bearings that we're going to use. We're going to use what is called a thrust bearing, and this takes axial loads like this but still allows it to spin. This is what will allow our disc to sit on top and spin like this. And it comes with three parts. It comes with two what are called bearing races, and then one which is called a thrust bearing. Just so when you're looking at a good vendor is McMaster Carr or Granger. You'll also need O-ring, because the O-ring is what allows the driving wheel. You'll put it on the driving wheel and it will use the O-ring to drive your sensing wheel from the motor. And I'll show you how to do that. And this is a 15/16 O-ring, just smaller than an inch. You'll need several machine screws. You need about 3 machine screws and 3 washers. If you can get electromagnet, you'll need an electromagnet. About 2 pounds worth of force is good. To protect your motor and your electromagnet, you'll need to acquire 2 film canisters, 35mm film canisters. And these are very difficult to find, but if you go to a Walmart and go to their photo place, you can actually ask them. They'll give them to you for free. You also need some wax. The wax is used to protect the motor from any water. You can get this at Home Depot. It's just toilet bowl gasket wax. One of the most important things that you need to get for your system to work is a Hall effect sensor. It's very small, it's hard to see. And a Hall effect sensor is just a few cents. You can get it at sparkfun.com or probably Radio Shack carries them. While you're at getting electronics, you'll need to get a tether cable. And this is a 12-foot tether cable, probably a little too long, but it really depends on the length that your ROV is going to be going away. Use the tether cable to bring all your information back to the surface. A few other things, you'll need some wood screws and some pieces of wood. This right here is called a thrust bearing, or not a thrust bearing, a bushing. This is a brass bushing. You'll need 2 of these brass bushings. It's a flanged brass bushing. It has a 7/16 inner diameter. You're going to get 2 of those. Those will reduce friction. You'll also have to manufacture a couple other pieces. Okay, so you'll need to get 2 different types of aluminum. You'll need to get a 2-inch bar stock. It's about a 1/4 inch thick. So you probably want to get 3/8 so you have a little bit of room to play with. This is an inch diameter and also a 1/4 inch. So I'll start with 3/8 inch again. This is a big chunk of aluminum. It's about 5 3/4 inch in length, 1.5 inches, and about 0.75 inches in height. And you'll use all of this bar stock to machine that. You can get that at like McMaster Carr, or if your local machine shop has one, perhaps hopefully you have one in school. So that's all aluminum, which is great to resist corrosion. These next pieces are made out of stainless steel. Don't try to use regular steel because it rusts. As you can see, my thrust bearings are made out of regular steel, and they've rusted a little bit. And these are just small bar stocks, about 1/4 inch in diameter, and you'll machine those. All the engineering drawings are in my document. You'll also need 8 small, powerful magnets. Try to use rare earth permanent magnets, about 1/8 inch in diameter, and we'll press those into here. And then finally, the last thing you need is a radial bearing. A radial bearing is very much like a thrust bearing, except for it takes radial loads. And you can get this at McMaster Carr or Granger also. The difficult thing about this is radial bearings require very close tolerances for when you are drilling this hole before you press it in. So I'd recommend getting a bearing that you know your machine shop has a reamer for. I made the mistake of getting a metric bearing when all my machine shop had it in inches, which made it difficult. I had to get some help from a technician to bore out the precise diameter. You need about 1/1000th of an inch worth of clearance. When you go to press all of this in, you'll use something kind of like this, probably make it out of steel. And all this is to push on the outside of your bearing. You do not want to push on the inside of the bearing, and that will allow you to press this in using a vice grip of some sort. So that's about all the materials that you need, and I'll show you how to press in these magnets. So to press in the magnets, it's very important that you test to see which side of the magnet works best with the Hall effect sensor. The Hall effect sensor only works with one side of the magnet, so be sure to test your magnet before you start pressing in, because you might find out you might press all your magnets and then none of them are detected by the Hall effect sensor. So what I did is I did 1 or 2, and I used a Sharpie and colored the end of it, of which side I wanted to press in. And then since all the magnets line up opposite ends first, you can only have to do 1, and then you can line the rest of them up. And then what you can do is, if you use like a steel vise like this one, you just, since your magnet loves metal, just attach it to your vise like this, assemble it in and put your hole in there, and then just crank down on this and it will just slowly slide in. You don't have to be as accurate with these holes as you are with the bearing, because aluminum's pretty flexible and allow it to go in pretty easily. So that's how you push in the magnets, and that's how you make your product. Okay, so we're going to start teaching you how to waterproof things. I'm going to show you how to waterproof the motor, then I'm going to show you how to waterproof some of your electronics. To waterproof a motor, what you're going to do is you're going to use this wax that we got, this toilet bowl wax, and after you've covered your motor in a tight coating of electrical tape, make sure to do that, because if you don't, the wax can get inside the motor and ruin your motor. So be sure to do that. Then once you've done all of that, you're going to take this wax and you're just going to slide it over your shaft of your motor like this, just like that. And you're going to take your film canister now, and after you've drilled a hole in the top right here, you're going to put your motor through there, and then when your shaft goes through, you're going to push tight, and what that will do is that will cause the wax to kind of go up around the motor and protect it. You're also going to take another ball of wax and put it at the top where your other connections are, because what that will do is that will do when I put this lid on right here and compress it, it'll do the exact same thing it did down there, but now push the wax all around my solder joints. So now I have my working motor. If you want to make it a little more waterproof, what you can do is you can put some epoxy right there, which I'll show you when I show you how to do the electronics. And that'll help further waterproof and keep this protected. Finally, once you're done with your motor, you're going to attach this your drive wheel. It looks like that. Should slide right over. Try to make it as close as possible. To make it actually stick to the motor shaft, though, you're going to use the exact same epoxy that we're using for the whole waterproofing. That's why I recommend getting it. And that will actually cause your wheel to stick to the motor, and it'll allow your motor to drive your sensing wheel. So that's how you do that. Now let's move over, and I'm going to show you how to waterproof the other stuff. Okay, so I'm just going to show you how to waterproof your electrical system and all the other components in your system. If you go get 5-minute epoxy, you can usually find it on Amazon. It comes with 2 tubes. When you mix the 2 tubes together, that's when it starts to harden. You got to make sure to get equal amounts. So what I'm going to do is I'm going to put a dot of each one, because I really don't need that much. When I did this the first time, I actually used quite a bit, and you don't have to. So put 2 drops on here. Be sure to be in a well-ventilated area because it smells. So you can kind of see they're about roughly the same size. You don't need to pull out, you know, a measuring system or anything. And then mix it all together. So what I'm going to do is I'm just going to put it in this hole, and the reason is because this hole leads to my Hall effect sensor. So if I put down this hole right here. And this is also a great way to protect any like soldering points that you may have made, or any junctions that you may have made. Like for example, when I first made my motor, I put it on the outside of the motor on the film canister to protect it from water coming in. So it kind of looks like that. I mean, you don't have to put very much in. And you let it sit. It'll take about 8 minutes, and then soon it'll turn into this hard one. So when I made the Hall effect sensor one, I had to put it on, and I had to kind of like massage it and keep it, you know, together with a toothpick. But that's actually not too hard, and I'd suggest actually doing it this way and trying to keep the epoxy up like this. It'll actually form a nice waterproof seal. And if it's too much for your wheel at the end of hardening, you can actually sand it down and make it pretty close to what you need, and so it'll actually do the job just perfectly. So the circuit's pretty easy to build. You have one voltage that you're really going to use, 6.5 volts. You're going to feed the positive in there and ground in here, and they're going to run this way. I have 3 different resistors. You have a 10 kilo ohm resistor right here, an 8 kilo ohm resistor right here, and a 4.7 kilo ohm resistor right here. Now if you remember your wires that you attached for your tether cable, this blue one is the one that I attached for the output of my Hall effect sensor, and this brown and white one represent the power for the brown and the white for the ground, and then these 2 are the motor, which I'll talk about later. So you take your output right here, and you're going to put it in between your 10 ohm resistor and your 10 kilo ohm resistor and your 8 kilo ohm resistor right there. And then the yellow is actually where you're going to feed out, and that should be about 1.7 volts when you have 6.5 volts coming in here. So it's pretty basic, pretty easy to construct. So that's it. So now we've actually built our viscometer, and so we're going to test it out and see if it actually works. So here we put our viscometer in our tank. You can see it down there. It has the motor spinning. You can hardly tell right now, but we run it out with a tether cable, and I've shown you already how to make your circuit. We use a power supply that has 2 different power settings, 2 different voltages. We have the 9 volts for our motor, and then about 6.5 or 7 volts for our Hall effect sensor. Be sure not to go over 7 volts for that, because you could ruin your Hall effect sensor. So, and then what we do is we read in the input from our Hall effect sensor right here into what is called LabVIEW. And LabVIEW will record a bunch of data as we do it. So let's try it out, okay? So LabVIEW has a data acquisition assistant right here and a write to file, and it'll just keep running through that while I click this play button. So let's go ahead and click the play button, and you kind of see what happens. So we click the play button, and we bring the disc in contact with the motor, and it starts spinning our sensing disc. And you let it spin down like that, and then you click stop on LabVIEW. Be sure not to click stop before your disc spins down. If you do that, you'll get really bad data. And then we'll test out our data. So I've written some MATLAB code, which is included, and if you update your file name, which is right here, and click play, it will spit out all of the important stuff that you are curious about, which is, this is the spinning down of my disc right here, the velocity of my disc, the angular acceleration of my disc, and this is just for kicks and giggles, the acceleration versus velocity, which shows kind of how non-linear it is. So that's how you test your equipment, and now we know that it's working, so that's the end of it, folks.